Hello, everyone. Today we have Lekai Chen here, giving a talk on their paper on large language models as probabilistic minimally adequate teachers for DFA learning. He is a PhD student at University of Colorado, Boulder. Yeah, we're excited to have you here, and you can take it from here.
Yeah, okay. Hello, everyone. My name is Lekai, and today I will be presenting my paper titled LLMs as Probabilistic Minimal Adequate Teachers for DFA Learning. So, uh, this talk is organized into four parts. The background of automata theory and related work on using LLMs as oracles and error corrections in membership queries, and also our proposed method for learning DFAs using LLMs and oracles. And the last part is empirical results. And let's start with the basics. What are automata? Automata are an abstract state machines designed for recognizing and computing formal languages. Examples including finite state machines, push-down automata Turing machines, and and Butcher automata. In this paper, we will focusing on uh, deterministic finite automata, which we also call DFAs, and and why should we care about automata and DFAs in the context of machine learning? So, automata, particularly DFAs, have several valuable applications. They can serve as reward machines in reinforcement learning. They're used for sequential data modeling, and they also support the development of in interpretable neural networks. But why we choose automata over other formal structures, there are three key reasons. I think the first is uh, the expressiveness of DFA for modeling sequential data. Second is uh, we can do verification and ensure its correctness, which are critical in many applications. The third is we value its existence of well-established automata learning algorithms. And finally, why we specifically focus on DFAs. The first reason is DFA have clear and predictable behavior uh, because it's deterministic, and second, the state space is manageable, making them computationally feasible, and we can handle it easier. And let me start by defining what a DFA is. A DFA is defined over a finite alphabet, which we call sigma, and we denote the DFA as A. And it's represented as a quintuple. A equals a tuple with five components, which are Q of a finite set of states, and sigma is a predefined finite alphabet, and Q0 is the initial state of the DFA, and delta is a transition function which takes two inputs, a state from Q and a symbol from the alphabet, and also DF is a subset state of A representing the final or accepting state. Now let's talk about terminology we use for the following algorithms. Uh, so first, uh, if A is a symbol from uh, alphabet and Q is a state, uh, then the state reached by applying the transition function denoted as delta of A applies Q, and A is called a successor of Q. A DFA process a word B, which is a sequence of symbols from the alphabet. It evaluates this word using a function denoted as A of Q, which maps the sequence of symbols from sigma to either 1 or 0. This output corresponding to whether the word is accepted or rejected by the DFA. And the DFA maps a word from maps a word U from the alphabet of all possible strings over sigma corresponding to a corresponding state. This is done through the function a bracket U equals delta applied to Q0 of A and U. And finally, M refers to the system under learning or SSU. This is the system or target automata we are trying to model or learn by DFA. Yeah. Yeah, now let's discuss how to learn DFAs. There are generally two main approaches, active learning and passive learning. In active learning, we use an oracle called minimally adequate teacher. This oracle can answer two types of queries, membership queries and equivalence queries. The learner actively interacts with the oracle, asking membership queries and equivalence queries to construct and refine a hypothesis DFA. And what is a membership query? A membership query checks whether a given word composed of symbols from the alphabet belongs to the target automaton. And what is an equivalence query? An equivalence query checks if the hypothesis DFA is equivalent to the target target DFA. Specifically, it asks whether there exists any word that produce a different result in the target automaton and the learned hypothesis. In other words, it looks for a word that one DFA accepts while the other rejects. And for using LLM as oracles, we aim to reduce redundant membership queries. To achieve this, we maintain two caches labeled as C to store previously queried words and their results. Okay, the second method to learn DFA is passive learning. In this approach, the algorithm infer a DFA using a fixed set of examples without interacting with an oracle. There are some key characteristics of passive learning. The first is passive learning rely heavily on state merging techniques to infer DFA. The second thing is some passive learning algorithms are designed to tolerate some noise in the data. And the last is, unlike active learning, passive learning does not provide strict correctness guarantees for the inferred DFA. And then let's talk about why we might use LLMs as oracles in the process of learning DFAs. There are several compelling reasons for this. The first is LLM are trained on vast and diverse dataset, which gives them a deep uh, reservoir of knowledge that can be leveraged during the learning process. And the second, they can perform well even with minimal examples, making them efficient for setting real data. It's not enough. Uh, and LLM excel at understanding and reasoning about sequences, which aligns well with the nature of automata and sequential data. Uh, First, their reasoning capabilities makes uh, them suitable for more complex queries and tasks. And last, by leveraging the built-in understanding, LLM can minimize the number of queries needed using the learning process. Now, while LLMs have clear strengths, there are also challenges when using them as oracles for DFA learning. The first is LLMs struggle with equivalence queries. Well, they perform well on membership queries. LLMs are less reliable when they handling equivalence queries. These limitations can make it hard to fully validate the learned DFAs. The second is incorrect responses. Because LLM are probabilistic language models, they cannot consistently provide accurate answers to membership queries. This can introduce errors into learning process. Uh, and we call these errors persistent errors. When LLM make mistakes, these errors can be persist. Unlike traditional deterministic methods, sampling additional responses from LLMs does not necessarily resolve these inaccuracies. Now let's now look at the current research utilize LLM in automated learning and some of the limitations these methods have. The first approach is direct transition generation. Some methods have LLM directly output the state transitions in the DFA. This means LLM predicts the next state given a current state and the input symbol. Uh, uh, Actually, it essentially builds the DFA from scratch. This approach is detailed in research by Alcide and others in 2024. The second one is using LLM as membership oracles. Another common approach uses LLM to answer membership queries. In this case, the LLM evaluates whether a specific sequence of symbols belongs to the target DFA, as explored in the work by Vasquez and colleagues. But why does it fail? Because this method feel some significant challenges. The first is they use naive zero-shot or few-shot prompts. Both of these methods rely on simple direct prompting of LLMs without sufficient contextualization or tuning, which limits their effectiveness. And second, they don't have the mechanism of error correction. This method cannot identify or correct errors made by LLMs, which can lead to persistent errors in uh, during the learning process. And last, there's no theoretical guarantee uh, to that this method will consistently produce correct or optimal DFA, making them less reliable to rigorous applications. Okay, now let's begin with error correction in active DFA learning. Several approaches have been proposed to address the errors during the learning process. The first is learning with noisy observations. Dean and colleagues in 1995 showed that it's possible to learn DFA in polynomial time, even when the observations are noisy. The key assumption is that the correct response frequency for any repeated query is more than 50%. This ensures that over time, the learner coverages to the correct hypothesis despite the occasional errors. And the second is proposed by Anglin in 1997. He introduced the learn anyway algorithm. This method can handle DFAs even with equivalence queries and malicious membership queries. However, it comes with a cost as counterexample grow longer and the system under learning becomes more complex. The error rate in the membership queries rises superlinearly. And for the third, Moeller and his colleagues in 2023 proposed the incomplete, minimally adequate teacher framework. Here, the Oracle has limited test and knowledge, while IMAT cannot answer all possible queries. It guarantees correct answers within its knowledge scope, making it a reliable option for certain applications. Now let's look at the error correction in passive DFA learning. While these algorithms are noise robust, they lack strict correctness guarantees. Let's explore why. The first is passive learning algorithms use state merging techniques, which generalize from the provided sample sets. This allows them to handle noisy data effectively, but by identifying patterns across potential noisy inputs. Second, unlike active learning, passive algorithms cannot refine their result through queries since they are limited to a fixed set of samples, and the inferred DFA might either be incomplete, failing to capture all valid behavior, or overfit, reflecting the noise or biases in the training data. Now, I will introduce our method, start with the math framework. As we discussed earlier, the framework consists two key components, a learner and an oracle. The learner interacts with the oracle by making membership queries and equivalence queries to infer the target DFA. However, as we highlighted in the previous section, the standard math frameworks struggles with persistent errors when LLMs are used as oracles to answer membership queries. To address this issue, we propose the probabilistic minimally adequate teacher, which we call PMAT framework. The PMAT framework allows errors in membership queries while still ensure the accurate equivalence queries. Let's break it down. The learner attempts to infer the SUL by asking map-tree queries and equivalence queries. The PMAT Oracle provides approximate answers to membership queries, while its responses may contain errors. It enables learner to progress despite the errors. Uh, and also the equivalence oracle. This oracle ensure accurate answer to equivalence queries, which are crucial for refining the hypothesis that might contain persistent errors. In the PMAT framework, the learner in the PMAT framework, the learner use counterexamples provided by the equivalence oracles to iteratively refine its hypothesis. This process continues until no further counterexamples are found. And then let me explain how we formally define the error rate in the PMAT framework. The error introduced by LLMs can be modeled as follows. So first, given a context which includes elements like alphabet sigma, and the description text description of the system under learning, the membership queries, and any types of prompts provided. The output distribution of the LLM oracle is modeled as O sub n Q of Q equals the probability that X falls between 0 and 1 given the context. This represents the probabilistic behavior of the LLM in answering membership queries. And second, sampling from PMAT framework doesn't provide exact outputs that align with the SUL. Instead, it converges towards the overall output distribution of the LLM, which may include errors. Third, the error rate for a specific membership query is denoted as epsilon of Q is defined as the probability that the output of the membership oracle is not equal to the true output of the system under learning, denoted as M of Q. Formally, this is expressed as epsilon of Q equals the probability that Q sub M, Q of Q is not equal to M of Q. The total mistake rates across all membership queries denoted as E is calculated as the average error rate. This is given by E equals to the sum of epsilon of Qi from I equals 1 to n divided by n, where n is the total number of membership queries. And our LAPR algorithm is built upon the triple T algorithm, which is currently the sort method for DFA learning. However, the triple T algorithm was specifically designed for classical math setting, where errors in membership queries are not allowed. And to address this limitation, Anglin in 1997 proposed the Learn Anyway algorithm, which introduced a framework for handling errors in membership queries. Let's break it down. So first, the learn anywhere algorithm is proved to learn DFA in at most L plus one iterations. Well, L is the size of the observation table. This size scales as a product of the alphabet size M and the number of the state N in the target DFA. And the second, these algorithms rely on the fact that equivalence query produce accurate counterexamples, while in membership queries ask about a word identical to one finding a counterexample. The This algorithm use a counterexample to correct the incorrect membership query result. And despite its strengths, the algorithm faces challenges with equivalence query costs, specifically as the length of the counterexample increases. The absence of identical counterexamples makes the process more computationally expensive. And therefore, we produce the large algorithms. The following notations are used throughout our algorithms. Uh, the first sigma, the alphabet used in the DFA, and the LA, the active learner that queries oracles, the passive learner, LP, used for hypothesis refinements, and membership query oracle OMQ. The membership provides answers to membership queries, and the equivalence query oracle OEQ, and the cache store from membership queries CMQ, and the cache for storing equivalence queries CEQ. And the LARP algorithm combines active and passive learning strategies to address the challenges of learning a DFA, particularly when working with noisy membership queries. Let's work through these steps. So first, the algorithm begin with active learning, where the active learner queries the membership oracle for a specific membership queries. This these queries help the learner start building a hypothesis about the target DFA. The active learner refines the hypothesis based on the counterexamples. And once, if the refinement process fails due to the persistent errors in membership queries, the algorithm transition into passive learning algorithm into passive learning phase. First we do a parameter search. A binary search and a linear search are performed over specific parameters to adjust the passive learning's dataset construction. The dataset are split into positive and negative examples sampled from the caches. And then we use the passive learner to construct multiple hypotheses based on the splitted data, and a voting mechanism determines the most likely hypothesis. And labels of top voted queries are reversed and are refined, are reversed and a refined passive hypothesis H sub p is constructed accordingly. And then the passive hypothesis is then checked with the equivalence oracle. If no counterexample are found, the learning process is complete, and the algorithm returns this hypothesis. Otherwise, the process look back, updating caches, and refine further. So for the passive refinement phase, is which is a crucial part of our LAPAR algorithms designed to handle and correct errors in membership queries. So the intuition for this mechanism is the idea is to sample dataset from membership query cache. If one of these subdata set contains uh, no con contains no errors, the hypothesis is derived from. The hypothesis derived from it is likely to identify the incorrect queries, and for the uh, voting mechanism for each query, the algorithms counts votes across the hypothesis built on the sample dataset. Queries receiving the fewest votes are flagged as incorrect. Their labels are reversed, and a new hypothesis is constructed using all cached membership query and equivalence query data. And uh, formally, the probability that a sample data set contains no errors is denoted as beta, calculated as beta equals to the number of combinations of n minus n choose alpha n divided by n choose alpha n, where n is the total number of unique examples in the membership query cache, and m is the number of incorrect queries. Alpha is fraction of the samples is the fraction of examples sampled. The algorithms use binary search to find an alpha value such that beta is greater than a certain value. The probability of having at least one error free data set across multiple samples is denoted as gamma, calculated as gamma equals to 1 minus the quantity raised to k, where k is the number of samples. K is determined via linear search to ensure that the gamma is greater than 0.99. And to refine the hypothesis further, the algorithm calculates the likelihood of merging states incorrectly and determines the number of states needed to achieve high confidence in the final DFA. So the number of tests required is defined by T, and for M merges and for and the probability P of an invalid merge, the number of tests T required to achieve a confidence level D is given by T equals to the log of 1 minus the quantity D to the power of 1 over M divided by the log of 1 minus P. And the probability P of an invalid merge is influenced by both the size of the sample dataset and the number of errors. It is calculated as P equals 1 minus beta. Okay, so the overconfidence D in the correctness of DFA after T test is calculated as D equals to the quantity 1 minus beta to the power of T raised to n. And finally, the confidence D star or uh, and finally the confidence D star is obtaining a valid hypothesis is suggested by the probability of having at least one error-free dataset gamma. This gives D star equals to gamma times T. This confidence adjustment ensures that the LAPA algorithm can iteratively refine its hypothesis and ultimately converge to a correct DFA, even when membership queries contain errors. So to enhance the LLM's ability to answer membership queries and thus speed up the learning process further, uh, we propose the verification prompt, which built on chain of thought reasoning in LLMs. Initially, the LLM answers the membership queries by providing an analysis based on the examples queries. However, because LLMs sometimes generate incorrect or irrelevant reasoning referred to as hallucinations. Um, these responses may not match the language definition or the query input. So to address this, the verification prompt introduce a second process. In this step, a teacher LLM evaluates the initial response, checking it against the language checking it against the language definition and the original query input. The teacher then outputs a structured JSON containing three components. Whether the analyze align with the language definition and whether it is consistent with the query inputs. And the reasoning process and the uh, third component, the reasoning process behind these conclusions. If any errors are detected, the system either corrects the initial response or adjust the prompts to further refinement. This verification prompt ensures greater accuracy and reduce errors. And we also introduce the discrimination prompt, which is designed to reduce the membership reduce errors in membership queries. And it is inspired by two facts. LLMs performs better when provided with examples rather than relying solely on direct reasoning. It is impractical to present all cached membership queries due to the LLM's limited context length. To address this, the discrimination prompt focuses on selecting the most similar queries from the cache to provide more relevant context. And then we talk about the intuition behind the similarities. The intuition of this approach is that the similar words are likely to share properties within the same language. However, identifying similarity isn't always straightforward. Let's look at the examples in the figure. The DFA in the figure accepts all the words start by A, right? And if the query is, for example, A B B B B B, and two cached words could be 6B. This is similar based on the added distance, as fewer changes are needed to transform it into the query. Uh, and and the second word A in cache is similar based on the property, as it starts with the same character A. And the challenge is to find a word that balance both the properties and added uh, to balance both properties and added distance for the most effective context. So to address these challenges, the discrimination prompt use the following steps. Uh, First, we build a discrimination tree, a tree structure to track membership queries and equivalence queries, organizing them based on their relationships. And then we do query positioning. For any new query, the algorithm determines its determining the algorithm determines its positions within the tree, essentially identifying the leaf where the query belongs. Uh, and then we do parent location. The tree is then used to find the lowest common ancestor, LCA, of the query's leaf, which helps to identify related cached queries. And then we select the words to prompt the LLM. From each child node of the ancestor, the algorithm selects words that are most similar to the query based on the added distance. This ensures a balance of similarity in structure and context. By okay, now by using this method, the discrimination prompts ensures that LMs are provided with only the most relevant cached examples, improve accuracy while staying within the constraint of LM's context length. And here's a detailed algorithm of discrimination prompt. It's kind of complex to explain it, so let's just skip it. So we compare different prompts to evaluate their impact on the query accuracy and learning performance. The baseline performance is shown high error rates and low learning accuracy. The baseline is just it's just using LLM to answer the membership queries directly without any prompting or resampling techniques. And then we compare the chain of thought prompt, which reduce the error rate to 0.068, improve the membership query answering accuracy slightly. And our verification prompt, which involves self-checking by LLMs, achieves the best error rate at 0.044 by enhancing query accuracy. And the discrimination prompt, which selects the most relevant examples, achieved a comparable error rate of 0. 0.47, but outperforms others in learning accuracy, reaching the 0 of 0.571 for triple T algorithms and 0.536 for L star algorithms. These results show that lower error rates correlates fewer required queries, demonstrating the effectiveness. Also, demonstrating the effectiveness of Triple T for minimizing queries and improving the learning success. Then we compare different algorithm performance under different prompting strategies. For L star and triple T, this classical DFA learning algorithms struggled with incorrect membership queries, leading to lower effectiveness in handling errors. And second, the learn anyway with triple T algorithms. These algorithms use counterexamples to adjust queries, achieving improved accuracy. However, it faced challenges with lengthy counterexamples in complex DFA settings requiring more queries. And LAP and LAPA with triple T algorithm, LAPA consistently formed equivalent DFA, even when faced suboptimal counterexamples. By using both membership query and equivalence query, LAPA corrected persistent errors caused by LLMs and achieved perfect accuracy of 1 across all prompting setup. And we further examined the membership queries versus error rates. The LAPA required fewer membership queries than learning anyway and maintain a stable number of counterexamples as error rates increased. So we can see in this figure, the blue line is LAPA with triple T algorithms, which is our method, and the origin line is learn anyway with triple T, and the green line is kind of upper bound, which we use a passive learning algorithm called RPNI EDSM to learn the target DFA, while we force it to continuously ask membership to ask equivalence queries to the oracle. So it's kind of different to classical passive learning algorithm. We just use it as upper bound, and so when error rates exceed to 0.18, the passive algorithms like RPNI becomes more efficient as they rely heavily on counterexamples rather than queries. And we also found that proper prompting with LLMs reduced the error rates below 0.1, making LARPA not only more efficient, but also comparable or superior in performance to both learn anyway and passive algorithms like RPNI and EDSM in this setting. And yeah, and that's it. Thank you everyone for your interest to my paper.